Homework pressure? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
For this question, we want to consider the maximum height a person can fall so that they don't break the bone. So the first thing we're going to do is we're going to figure out the effective spring constant of treating the bone like a spring. So according to Hooke's law, force is equal to K times the change in length. In this case, we could call that delta L. Well, that means that K is equal to well, actually, let's consider it like this. So F is equal to K times delta L, but F is also equal to the Young's modulus Y times delta L over L naught multiplied by the area, A. So if we solve for K, we find that K is equal to AY over L naught. Well, we can also see that in general, from Hooke's law, x squared is equal to force over spring constant K. Well, if we plug in the value for the spring constant, what we have here, so that's x, actually, not x squared, excuse me. This is x is equal to force over the spring constant K. So this is equal to force times L naught over A times Y. Now, the reason this is important is we're now going to use energy conservation. So the energy potential due to gravity, which is mgh, is going to be equal to the energy stored in the spring, or the bone, 1/2 kx squared. So if we substitute in our value for k and our value for x, and we solve for h, we find that h is equal to 1/2 mg multiplied by, since x is squared, we have f squared times L naught divided by A times Y. So even though x is squared, which would give you an L naught squared over an A squared Y squared, K is equal to AY over L naught. So those squares cancel, and this is our expression for the height. Plugging in those values, we get 0.56 meters. Which we can go ahead and box this in as the solution to our question.